So today we are starting with the second lecture of this lecture series on work, power, energy. So today we will be seeing the energy. So I'll write the heading. So what is energy? Energy is defined as the internal capacity of the body to do work. And this is the only definition which you have to keep in mind while you are seeing the questions of energy. So what is energy and what are the different types of energy? Okay, no need to tell. You have learned the kinetic energy, you have learned the potential energy in your 10th grade. Now you will be seeing in 11th and 12th many energies such as heat energy, thermodynamical energy, electrical energy and various energies. Okay, so these are the different types of energy. You will learn these all energies subsequently in different chapters to come. In this chapter, the work, power, energy, we are concerned with the kinetic energy and the potential energy. Okay, so now we'll see what the different types of energy. But before proceeding to different types of energy, we'll see the Einstein's energy mass equivalence. Okay, so what is energy? Energy is defined as the internal capacity of body to do work. So this is the energy, and this is the definition is enough to define what is energy. Now I've told you there are various forms of energy such as heat energy, electrical energy, potential energy, kinetic energy. Now we'll move on to the next topic, which is the Einstein's energy mass equivalence. Okay, so what is Einstein's energy mass equivalence? You can understand this was given by Einstein. Next is energy mass equivalence. Equivalence means similar or equal to. So here you can see two terms, one is energy and another is mass. So Einstein gave an expression which could equate these two terms, one is energy and one is mass, with a simple expression, that is E is equals to mc square. There has been no any proof to prove this expression, but this expression has been experimentally proven in many of the cases. So we will see what is the expression and which two terms did he equate with this expression. So energy, which is given by E, he equated it to mass, and conversion factor was c square. So the final expression for the Einstein's mass energy equivalence I can say is E is equals to mc square. Means I can say that mass can be converted into energy as well as the energy can be converted into mass. Okay, like this is earth, okay, and this is sun. So rays from the sun are falling on the earth. You can say that the rays from the sun carry some amount of heat energy in them, and that heat energy falls on our earth, and that heat energy is going to get converted into some amount of mass. So I can say that some amount of mass is going to get deposited on the earth, and this is the reason why we say that the mass of earth is increasing day by day. Okay, so this is the reason I am telling you why is this E is equals to mc square such a very great expression, because it equates energy with mass. Okay, and the conversion factor is c square. Now just let's extrapolate this expression to some new details. So the expression is E is equals to mc square. So tell me, mass is in kgs, c square, which is the speed of the light, it is meter per second square. So I can say that E is equals to kg meter square per second square. So here mass is mass of object and c is the speed of light, which is nothing but 3 into 10 raised to power 8 meters per second. So in this way we have known what is Einstein's energy mass equivalence. Okay, now we will move on to a next topic. So now we'll move on to our next topic, which is kinetic energy. So what is kinetic energy? The definition of kinetic energy is the internal capacity of any object to do work with virtue of its motion. Okay, so this, from the definition you can understand one thing, that this is the energy which is possessed by an object which is in motion, because the definition says by virtue of its motion. So this is the energy which is only present in a body which is in motion. A body which is at rest cannot have any kinetic energy. Okay, so we will see what is kinetic energy. So kinetic energy is defined as internal capacity of any object to do work So this is very important term, motion. This defines that kinetic energy is possessed only by those objects which are in motion, and it is not possessed by all the objects which are at rest. Okay, so the expression of kinetic energy is half mv square. So kinetic energy possessed by any object is equals to half into mass of that object into velocity of that object. Okay, so this is the expression for kinetic energy. This is one form of energy. So the dimensions and the unit will remain same to the energy, whichever it be potential energy, it be any other different energy. Okay, so this is how we have completed one of the most important topics, that is the kinetic energy. Okay, so now we'll see next topic, that is work energy theorem. So now we are going to see a new topic, which is work energy theorem. Before starting this topic, work energy theorem, I must say that this is a very important topic concerned with the NEET examination, because work energy theorem, the questions asked will be mostly solved by this work energy theorem. As well, applications of this theorem will be used in different chapters and its applications are widespread. So learning this topic is a prerequisite to attempting your questions in NEET examination. So let's learn it in a little detail. So I'll write the heading work energy theorem. Okay, so this is the most important theorem, or one of the most important theorem in physics. Okay, so what is work energy theorem? So you can see from the heading work energy theorem, so these three terms. So it's a theorem which expresses work in the form of energy. Okay, or it equates the work done by any object or on any object in the form of kinetic energy. Understanding? So what is the definition of work energy theorem? Work energy theorem says, or work energy theorem is defined as the work done by any object or work done on any object by any force, be it conservative force, be it non-conservative force, be it external force, or be it internal force. Work done by any of these forces on the body is equals to change in kinetic energy of the body. So I can say vice versa, that whatever change in kinetic energy will be there in the body, it will be equals to work done by all the forces which are acting on the body in its journey. Okay, so this is the definition of work energy theorem, and it encompasses all the works, be it conservative energy, be it non-conservative energy, be it external energy, external force, or any internal force. So each and every force will be encompassed in this theorem, and this makes it more special. So what does work energy theorem say? Work energy theorem say work done by all the forces. So all the forces means they can be conservative force, they can be non-conservative force, they can be external force, or it can be any internal force. work done by all these forces will equate to the change in kinetic energy of the body. So work done by all the forces, which can be conservative, non-conservative, external and internal, can be equals to So this is the expression, this is the definition of work energy theorem. Now we'll go in a little detail and we'll express it mathematically. So work total acting on any body can be equals to work done by all the forces, or I can write work done by all forces. And I know these forces can be conservative force, non-conservative force, external force and internal forces. So I can write work done by all forces means work done by conservative force plus work done by non-conservative force plus work done by external force plus work done by internal force. So this is work done by all the forces, which we represent this way, is equals to change in kinetic energy, change in kinetic energy of the body. So I can write this change in kinetic energy of the body as K final, Ke final, kinetic energy final minus kinetic energy initial, which will be equals to work done by all forces. So this is the final equation of work energy theorem. So I hope you have understood the work energy theorem. So again, work energy theorem says that work done by all the forces, which can be conservative force, non-conservative forces, external forces and internal forces. So work done by all these forces will equals to change in kinetic energy, which is kinetic energy final minus kinetic energy initial. So in this way we have completed the work energy theorem. Now we will move to the next topic, that is how to use this work energy theorem and how to solve problems based upon work energy theorem. So now we are starting how to use work energy theorem in different questions and numerical problems. Okay, so we will write how to apply work energy theorem. So how to apply work energy theorem? So the answer to this lies in some few steps which I will be telling. You have to apply these all steps to your questions, and I hope that your questions will not be wrong. So first is assign final and initial positions of the body. Okay, so assign final as well as initial positions of the body. What does it mean? Suppose I am just releasing a ball from some height. So the height from which I am releasing the ball will be the position initial. Okay, and the last position of the ball will be the ground, because it is going to touch the ground. So in this journey from ball, from top, from the point where I am releasing to the bottom, that is the ground, so I'll assign initial position as the point from where I am releasing the ball, and final position will be the position where ball touches the ground. So this is how we assign final and initial positions to the object. Okay, so this is the step number 1. Now second step is draw a free body diagram of the object So the next point is, draw a free body diagram of object when the body is passing between initial and final positions. What does this point means? Suppose this is a ball and I am dropping this ball from certain height. So the ball is dropped, this is the first position or initial position. Next, the ball will go down and ball will then touch the ground, which is nothing but the final position. Between these two positions, the ball will perform a journey, a vertical journey. So I want you to just pause this journey for a second. So you can pause this journey anywhere between the ball falling off the releasing of the ball and just ball touches the ground. So between these two, suppose if the ball is in middle, I want you to capture that movement and draw an FBD. Okay, so what does FBD means? FBD means free body diagram. Free body diagram is a diagram in which you denote all the forces which are acting on the body. Okay, so how we'll draw a free body diagram? Suppose now the ball is falling. Now a ball which is falling, how many forces act on the ball? In ideal conditions, the forces can be the gravitational force, but in some non-ideal conditions there is also a air drag. So additional force which can be a air drag force, and simultaneously the work done by this air drag force will account into matter. So the next point is, draw a free body diagram of an object when the body is passing between the initial and final positions. Now we'll write a third point. Third point says, find the initial and final positions of the body. Okay, so how will you find the initial and final position of a body? For this you'll require initial and final velocities. So you have to see what is the initial velocity when we have dropped the ball. That will be equals to 0 in that specific case. But if there is suppose another case, you have to find the initial velocity and find subsequently the kinetic energy. So this will be your initial kinetic energy. Suppose now the ball is on reaching the ground, has some velocity. So that is the final velocity, and that kinetic energy will be called as the final kinetic energy. This way you will get two different kinetic energies, the kinetic energy initial and the kinetic energy final. When you will subtract this, you will get change in kinetic energy, which will be equals to work done by all the forces which you can depict or which you can denote in the free body diagram. Okay, so these three are the most important steps in the work energy theorem, and these three steps are sufficient to make you solve questions on different types of work energy theorem. So now let's take an example which will clarify your concepts of work energy theorem. So now we'll take an example which you have seen earlier. I have a ball. I am dropping that ball from a certain height h. Okay, this is a ball. So this is the ball and I am dropping it from a height h. Okay, so this is the ground. Now I am dropping the ball from height h. So tell me, now we'll go to the first point. What is first point says? Assign the initial and final positions of the object. So our object is the ball and its initial position is this. So this is the position 1 or initial position. Now we have to assign the final position. The body reaches at this point on the ground, and this is called as the position number 2 or final position. Now what is the next step? Next step is draw a free body diagram of that object when it is passing between the initial and the final positions. So suppose if this is the journey, I take any point and I draw this body, and now I am going to draw the free body diagram of this body at that particular instant. So now tell me, what are the different types of work, different types of forces which you are going to see in this free body diagram. So first will be gravitational energy. Okay, so this is the gravitational force. So is there any other force? Yes. In non-ideal conditions there will be other force which is called as the resistive force. So in this particular case I can see only two forces. One is the gravitational force and the second is the resistive force. So I'll write the third point. Okay, suppose at this position, now what does the third point says? Third point says that draw or find out the initial and final kinetic energies. So where will I get the initial kinetic energy? At the initial position. Where will I get the final kinetic energy? At the final position. So I have to find the initial kinetic energy. So initial kinetic energy, initial is equals to half mv square. So this I'll write as Vi. Here the kinetic energy final will be half mv final square. So this is how I have written all the 3 points. Now what is the fourth point which I haven't told, but it's not that important to be told. The third point is, now you can equate the work done by all the forces which you can see in this free body diagram equals to the change in the kinetic energy, that is Ke final minus Ke initial. Okay. So if I rub this diagram, now I know that work done by all the forces, all forces is equals to work done by gravitational force plus work done by resistive force is equals to change in kinetic energy, which is half mv initial square minus half mv final square. So this is the most important expression which we have got in this particular expression. So this is how we are going to see, or we are going to solve the problems, numerical problems or work energy theorem. It is very simple. Whenever there is a numerical, just put work energy theorem into that particular question. You have to just solve it with these 3 important steps and you will get your answer. So in this way we have covered the work energy theorem and how to apply this work energy. Now we are going to see a next very important topic. What is conservative and non-conservative forces? You will see there are many times in work energy theorem you will have come across conservative forces, non-conservative forces and work done by them. So what is a conservative force and its difference from a non-conservative force? Okay, so now we'll see in detail what is the difference and what are the details of conservative and non-conservative forces. So first I'll write conservative force. So I have written heading conservative force. What does a conservative force means? Conservative force, from it is the word itself, conservative. It is going to get conserved. The work is going to get conserved. Okay. So conservative forces. What is a conservative force? The conservative forces are those forces which are dependent upon the initial and final positions, and they do not depend upon the path taken by the body to go from path position 1 to position 2. I'll repeat again. Conservative forces are those forces which do not depend upon the path taken by the body, but only and only depend upon the initial and final states of the body. Okay. So first most important point is the work done by conservative force depends upon initial and final position. Okay, and they do not depend on path taken by the body to go from position 1 to position 2. So these are the most important points which you shall know before you are learning conservative force. So conservative force is a force such that the work done by such a conservative force depends upon the initial and final position, and it does not depend upon the path taken to go from position 1 to position 2. So this is the general idea about conservative force. So what are different examples of conservative forces? So all such forces which depend upon the initial and final path are the examples of conservative force. Suppose this is suppose any object. So I take this object from this point to this point. So there will be some change in the potential energy. Okay, so there will be some initial potential energy at this point and there will be a final potential energy at this point. Okay, so suppose I now take this duster from another path. Suppose I take it from this path, okay, and put it at again at the same position. So now tell me, what is the change in potential energy? So your answer will be, there will be the change in the potential energy will be exactly similar to the change in the potential energy which I did earlier, because the potential energy is a conservative force, okay, or the potential energy which is due to the gravitational force is a conservative force, and the gravitational force being a conservative force, the work done depends upon the initial and final position and does not depends upon any path taken to reach the final position. So the gravitational force is one of the examples of conservative force, and this is the example you can remember whenever you fail to remember this concept. So if I write the examples, I can write gravitational force, then I can write electric intensity. So in such all cases, the work done depends upon initial and final path, final position, and does not depends upon the path taken. Extrapolating this conservative force and these 2 points which we have learned now to a new thing. So now tell me, suppose this is an initial position, this is the initial position, okay, so this is a point A, okay. Now suppose the particle goes from this point to this point to this point to this point, and now again it goes and returns to the same point, okay. So I also can call this as point B. This is the final position. So you can see that initial and final positions are same. So I will write initial position is equals to final position. Okay. So this type of paths are called as a circular or a return journey. Circular not by its shape, it is not a circular, but you can call it a return journey, okay, because the particle is starting from point A, it is going and again culminating in the same point B. So the initial and final points are the same, and this is called as a return journey. Like you go from home and again return your home, so this is called as a return journey because you start from the same point and you end your journey at the same point. So such journeys are called as a return journey. So tell me, what will be the work done in this journey? So in the case of a force which is conservative, in the presence of a force which is conservative, if the particle is performing such a return journey, then the work done by that force on the body or work done by that force will be 0. Why? Because my initial position is same, my final position is same, and I know that conservative force, work done by conservative force depends upon the initial and final states and not upon the path taken. So let the path be any, but my initial and final positions, if they are same, my initial work or final work are going to be same, and when I subtract them, it is going to be 0. So in such cases, if I write in return journey which is in the presence of a conservative force, your work done will remain 0. So work done by conservative force in return journey is 0, because the initial point and final point are same, and I know conservative force is one force for which the work done depends upon the initial and final position and not on the path taken. So whatever be the path, but the initial and final positions, as far as they are going to be same, the work done by the conservative force in the any conservative force is going to remain 0. Okay, in this way we have known what is the conservative force and what are its example. Now we will shift to the another type of forces which are called as the non-conservative forces. Now we are going to see the next topic, that is the non-conservative forces. So what are the non-conservative forces? So the again 2 points which will tell us how non-conservative force are different from the conservative force. So conservative force, as you know, they are the path independent, but they are the initial and final state dependent processes. But implicitly we can say the non-conservative forces are the forces which depend on the path. So they are path dependent forces, they depend on the path taken. So if you will change the path from going from first position to the final position, if you change the path, your work done by the non-conservative force is going to change, and it is independent of the initial and final positions. Okay, so it is the one which is path dependent. So if they are the positions, position 1 and final positions. So if it is a conservative force, if you go by any path between these two forces, and if it is a conservative force, the work is not going to change. But when the force is a non-conservative force, and if the point remains the same as in the case of conservative force, and you change the path, the work done by the conservative force in each and every path or each and every process is going to be different, because these are the forces which depend upon the path. So I'll write one of the points. So the non-conservative forces produce work which are dependent upon the path. Okay, so suppose this is the initial point, this is the initial point, and this is the final point. Okay, now suppose I go in a straight line. So this is a first case. Okay, now I go in, suppose this path, this is a second position, and now suppose I go by this path, this is a third case. So here work done in first process is not equals to work done in second process, and it is not equals to work done in third process. But if it would have been a conservative force, the work done in each and every process, that is 1, 2 and 3, would have been same. But as it is a non-conservative force, the work done in first is not equals to second, and it is not equals to third. Work done from going from initial point to final point changes with the path taken. This is the non-conservative force. Now we will see what is the work done by a non-conservative force in a return process or return journey. So what is a return journey? I have told you return journey is one in which the initial and final points are the same. So suppose this is the initial point, okay? And now the body goes and again comes to this position. So this is also a final position. I have told you the non-conservative force is exactly opposite of a conservative force. Conservative force is the one in which in return process the work is 0, or it is the process in which depends upon the initial and final states. But here it does not depends upon the initial and final states. Okay, it depends upon the path taken. So when it goes from initial position to final position, the work done will not be 0, but work done will have some value, and this value will increase with increase in the path taken from going from position 1 to the final position. Okay, so the work done here by all the forces or the non-conservative force is not equals to 0. There will be some suitable considerable amount. So this is the non-conservative force in case of the return journey. Okay, so what are the examples of a non-conservative force? The most important example for non-conservative force is friction force. So tell me, if you go from your home and again come to your home again, is friction produced will be zero? No. So this is what you have to know from a return journey, that even though if you perform a return journey in case of a non-conservative force, your work done by the body is not going to remain zero. So what are its examples? The examples are frictional force, so any resistive force, resistance will increase with the increase in the path taken. So these are the examples of the non-conservative force. Okay, so if I just now we'll study and now we'll find out the difference between the non-conservative and conservative forces. So the conservative force and a non-conservative force. So in non-conservative force, first point, in non-conservative force, the first point is depends upon initial and final position. But in this case, it does not depends upon the initial and final position. So I'll write does not depend upon initial and final position. Okay, next point is, I have told you, next point is it does not depend upon the path taken. But in this case it depends path taken. Third point is return journey. So in the case of return journey, work done here is zero because you know initial and final points are same. But in this case, in the case of return journey, the work done is not equals to zero because it depends upon the path taken. So work done in this case is not zero, whereas in this case it is zero. Next is, I'll give you examples. Example is a gravitational force. And in this case the example is frictional force. Okay, so this was a summary of conservative force and the non-conservative force and difference between them. Hope this table makes you summarize all the points in one go. Okay, now going on to the second point, the next point is potential energy. We have already seen kinetic energy. Now we are going to see potential energy. So what is a potential energy? So what was the definition of kinetic energy? Kinetic energy is the internal capacity of the body to work by the virtue of its motion. Okay, so it was dependent upon the motion. If the body is at rest, the kinetic energy is zero. If the body is moving, the body will have some kinetic energy. So if the body is in motion, there will be kinetic energy. But in the case of potential energy, the definition changes. What is the definition of potential energy? Potential energy is defined as the internal capacity of the body to work by the virtue of its position. So this position is now a very important term. So I'll write it is the internal capacity of body to do work by the virtue of its position. So the position is the most important point. So if the body has different positions, the potential energy it will possess will be different. The next most important point which I want to tell you is potential energy is a relative quantity, okay, but kinetic energy isn't. So potential energy is a relative quantity. So if I ask you what is a potential, so what is, suppose I give you a situation and I ask you what is the potential energy of any particular body or any particular object. So the question is invalid because the potential energy is a relative quantity. The question is wrong because question is incomplete. I have to ask what is the potential energy of a body with or object with respect to some surface or with respect to ground. So this with respect to is a very important term because potential energy in itself is a relative quantity. If I don't tell a potential energy or if I don't measure a potential energy with respect to some frame or with respect to ground or with respect to any surface or with respect to any body, it has to be with respect to some other thing. Otherwise the potential energy is invalid. Okay, so whenever you are asked potential energy, it has to be with respect to some other thing because the potential energy is a relative quantity. Now suppose a particular body will have a different potential energies with respect to different objects. The potential energy of that object with respect to me will be something, and that potential energy of that object with respect to any other person will be different. Hence potential energy is a relative quantity and it always has to be with respect to some any other object or any other point. So this is the importance of this point, that potential energy is a relative quantity. Okay, next is potential energy is only applicable in conservative force field. So this is a very important point. Potential energy can't be defined in a non-conservative field. It always can be defined only in a conservative force field, which you will know later on. So these are the must know points about the potential energy. Now we'll go to the numerical aspect or some expressions about potential energy which will help us to solve the numericals. So now we are going to see the numerical aspect, okay, of potential energy. So potential energy is given by U. Okay, so I'm going to write an expression F conservative. What is F conservative? I have told you potential energy is defined only in the case of a conservative force field. So the force given here is a conservative force, and that will be equals to negative gradient of U. Okay, so this is given by a special symbol, that is minus dou U by dou x I cap minus dou U by dou y j cap minus dou U by dou y z k cap. So what is this dou? We have previously seen du by dx or du by dy or du by dz. They were the complete derivatives or the full derivatives. But here you can see dou u by dou x. This dou is a partial derivative, and you will know how to solve the problems when there is a partial derivative further. So for now you can understand that the conservative force is minus dou u by dou x I cap minus dou u by dou y j cap minus dou u by dou y dou z k cap. Okay, so this is the most important expression which you have to remember. Now we are going to see the next thing. We are going to see a graph which is very important with respect to examination point of view. So I'll draw a graph. So it has been observed that this is the r. What is r? The distance between any two points or a distance of an object with respect to any other point. Okay, so this is r, or the distance of separation. If you go up and you go down, so here u is negative and here u is positive. Here it is a repulsive field, and here it is an attractive field. Okay, so this is the graph which you have to keep in mind, okay, because this graph is not going to change, it will be same, and you will be asked questions depending on this graph. So what conclusions can we draw upon this graph? Okay, so first is conclusion number 1. So the first conclusion is that when there is a repulsive field, your U will be positive. Okay, so when there is a repulsive field, your U or potential energy is going to be positive. Okay, now here you can see when there is an attractive field, the potential energy will be negative. You can see the graph of repulsive field lies above the x-axis, that is, it lies in a positive y-axis, whereas the attractive field, the curve for attractive field lies below the x-axis, that means it is a negative y direction. So I can write a attractive field has U which is negative. So whenever you get a negative U, that is negative potential energy, you are going to say that the field is attractive. But when you are going to get potential energy positive, we are going to say the field is repulsive. So this is one conclusion which you can draw from this graph. Okay, so what is the next conclusion? Conclusion So the second conclusion. So what is the second conclusion? Now tell me, as you are increasing the distance between the two bodies, means you are increasing the r, and if you are increasing the r, you are going along the positive x-axis. So as you are going along the positive x-axis, you can see this graph is increasing, means the value of U is increasing. Means I can say if you increase r, okay, if r is increasing and if you see that U is also increasing, if U is also increasing, then I can say it is a graph of a attractive field. Yes? Again I will say, if you are increasing the r, that is distance of separation, and if you see U is increasing with that r, okay, so I am going in this direction of positive y-axis, and in this graph I am seeing that the value of U is increasing. Here it will be -5, here it will be -4, here it will be -3, and go on, and it will become increasing, increasing and increasing. Okay, so in such cases, if you see r increasing and it with simultaneously you see U is also increasing, then you can deduce one thing, that the field is attractive. Next conclusion, if again you see if r is increasing but you see U is decreasing, so which of these both graphs you can see U increasing? So it is this graph in which you can say with increasing r the U is decreasing. Suppose here it is +5, here it is going to be +4, +3, +2 and so on, it will go on decreasing. So with increasing r, if you see a decreasing potential energy, then it will be this graph, and I know this graph is a repulsive field because it lies above positive y-axis. So it is a repulsive field. So these are two conclusions which are very, very important with respect to this graph. So this is the one graph which you have to understand and keep it in your mind so that you can solve most of the questions which come